Hi, our topic for today is properties of sets. So last time we defined sets, operations among them, and now we're going to see what are the properties that these operations have, and also how to prove or disprove some of these properties. So the main strategy here when we prove things about sets is the element argument. And instead of talking heavily about it, I'll just illustrate it on an example. But in that example, you will see that very often we use propositional statements from chapter 1 to justify the passages in our proof. But one of the main errors that happens, and that's what you need to kind of control all the time, is the following: to make it sure where you are. What is the type of your current object? Is it a set or is it a statement? So here it is. If it's sets, between them you use intersection, union, difference, complement. If they are statements, you use conjunction, disjunction, negation. Also here you have say equal, and here you say equivalent. So make it sure that you don't apply wrong symbols. They are analogous of each other. Intersection is actually connected with conjunction, union with disjunction, and so on. But they are connected, but they are not the same thing, and you shouldn't mix them up. Let's see an example. What would that be? 3 to 1. Prove that a subset of A union B intersection A. Proof. Let X belong to A. Generally, according to definition of being subset, we need to show that arbitrary element from left side belongs to the right side. So let X belong, that's our element argument. You pick up an arbitrary element, X arbitrary but fixed. That's the language from Susanna App's book. Arbitrary but fixed. And now I talk about that element. Then I will say the following. Okay, so first line, X belongs to A. Now the second line, X belongs to A, implies that X belongs to A or X belongs to B. Why is this true? Actually, I'm using the logic here, and what is the logic? That this is tautology. P implies P or Q, where P stands for X belongs to A, so this is your P, and this is your Q. Since this is tautology, this is correct conclusion. Using modus ponens from 1 and 2, I will get X belongs to A or X belongs to B. So modus ponens, and here's my justification, modus ponens between 1 and 2. So this is also an exercise for proving. What now? Number 4, X belongs to A union B. Why is that the definition of union? So if someone belongs to one of the sets, then it belongs to the union. Then number 5, what do I get? Since I have that accumulation of hypotheses, if I have X belongs to A and X belongs to A union B, then I have what? X belongs to A union B and X belongs to A. So what is this? I use the argument. If I have P and I have Q, then I have P and Q, and I have both of them. Number line and 1, 4 accumulated gave me their conjunction. And number 6, if X belongs, but look at this, these are all statements. This is statement about sets. This doesn't have a, this is just true or false. So these are statements, you see, and that's why between them I write or and. What about, why am I writing union here? Because this is the object and this is simple statement like P. X belongs to a set. So this is just a statement. Basic propositional statement in a way. So what would that be now? If I have that x belongs to both of them, then x belongs to their intersection. What is this definition of intersection? Here it is. From the assumption that x belongs to the left side, I derive that x belongs to the right side. So that's why, according to the element argument, A is subset of A union B intersection A. All right. That's how we prove using the element argument. And using this reasoning, we can prove some statements about sets. And those statements I listed in the notes. I'm not going to copy them here now. Or maybe I better do so that you don't think that they are irrelevant. So at least I will write the left column because the right one is the dual. So set identities. So using the element argument, people were able to prove, and I can actually ask you to prove some of them on your exam. A union is A union B is B union A, commutative law, associative law, A union B union C equals A union B union C. Oh, this one is interesting, it's called absorption law. A union A intersection B is just A. If you have repetition of one of them twice, then that's what the result is. And then distributive law, A union B intersection C equals A union B intersection A union C. It's like distributive law, usually whose outside gets inside twice, whose inside goes outside. And then what else? A union empty set is a union, a complement is universal set. And then the Morgan's law, A union B complement equals A complement intersection B complement. And there is one more list of dual ones. I'm not going to put them on the board. We have them in the notes. How does the dual look like? Let me make a dual of this one. So what do? Wherever you see union, you write intersection. So you get A intersection B union C equals A intersection B union A intersection C. How about this one? What is the dual of this one? A intersection A complement equals empty set. The dual of union is intersection, dual of universal is empty set, and the other way around. So I have the other one. So what now? These set identities are the same as identities that you learned in algebra. So in the future, when I need to prove something, I can do two different things. One, to go by the element argument, or the other one, to use these identities from this list to justify my argument. And sometimes, if I specify in the exam, prove by using the element argument, then I'm not letting you, or you're not going to get full credit for using identities. But if I just don't specify anything, that means they are both good. All right. Now what? Let me show you how do you prove how do I prove, actually one more. I better do 3-2-3 first, different than in my notes. So 3-2-3 example. 3-2-3, what do I need? It says, prove the set equality A intersection A union B equals A. It's actually this one. Not just the one, blue one, that would be here. So how do we prove that? Of course, if I ask you this on the exam, you cannot just call it and say, oh, that's one of the set identities from our notes. So obviously here, I'm asking you to prove that using the element argument. So I cannot use the identities if I need them later on today. I'll just quote them. So when you show that two sets are equal, you need to show a little more than what we did last time. And that is, you need to show if someone belongs to the left side, must belong to the right side, and the other way around, if it belongs to the right side, it has to belong to the left side. Sometimes we can go with a backwards argument and just show the arrow going up, so that the same argument, you don't repeat the right thing, but make it sure that that's legal. So let me see the proof. So what? Let me assume that x belongs to the left side. That means x belongs to the A intersection A union B. Then what happens? If x belongs to the intersection, then I know that x belongs to A and x belongs to A union B. And then what? So now I have x belongs to the A and I'm done. X belongs to the right side. Did I use some logic here? I use very obvious logic, but if I want to justify it, what would it be? P and Q implies P. If I have both of them, then I have each of them individually. So that's it. Or we can say one direction. What would be the other direction? Assume that x belongs to A. So x belongs to the right side. X belongs to A. Now I need to show that x belongs to the left side. Generally, that x belongs to the left side is exactly the same as what we had in that introductory problem, but doesn't matter, I will repeat it here. So let x belongs to A, then what do we have? X belongs to A or x belongs to B for the reason that I mentioned a minute ago. Then what? Now if it belongs to or, so this is because P implies P or Q. And then what? Then x belongs to A union B according to the definition of the union. Now if I call those two, x belongs to A and x belongs to A union B, so x belongs to their intersection. Okay, as I said, that was the same as when it x belongs to the left. So whenever it belongs to the left, it belongs to the right. Whenever it belongs to the right, it belongs to the left. This is the full proof. All right? Let me show you one more example. On the next example, I want actually to use the identity. So how do the proofs with the identities look like? They are much quicker and easier. So once you know identities, actually they are more like calculation in basic algebra. So example 324. It says the following: A set minus A set minus B equals A intersection B. By the way, sometimes I ask you, here I just said prove this. So if I ask you to prove, you can start proving immediately. If I ask you prove or disprove, it might be a good idea to draw a Venn diagram. And that Venn diagram is not a proof. It just gives you an assurance or gives you a hint how things look like. So here it is. This is A, this is B. So A set minus B is this. Okay? And then when I remove that from A, I actually get this guy. And that's exactly what it says. It's their intersection, so looks good, but let me write the proof. Here's the proof. Left side equals A set minus B, which is A set minus, so we know that A set minus B is the intersection B complement. So then I will use that twice, so it will be A set minus A intersection B complement. And that would be A set minus anything is intersection with the complement of that anything. Same reasoning. What would it be? It would be A intersection. Now I use De Morgan's law. I get A complement union B complement complement. So De Morgan's law says intersection becomes union, complements get attached individually. So what would that be? This is A intersection A complement, B complement complement is just B. And now I use distributive law, it's A intersection A complement union A intersection B. A intersection A complement is empty set according to our list of properties. A intersection B, empty set union anything, is that anything? Here it is. We proved that this is the right side. So see here, I didn't have logic, I didn't have reference to logic. I actually just used the rules from the list of identities, and that's kind of, actually, I'm not saying this is easier, but just easier to justify, so it's not like, you know, where one can make easily errors for not quoting the proper propositional statement. But so I noticed that students like this one more than the other one. All right, then example 3 to 5. They said what? Simplify. So I don't tell you this time what is it equal to, they just say simplify. And that would be A when you remove A intersection B, intersection B when you remove A intersection B. So in algebra, people would say that, oh, they just ask you to calculate this. So how can we calculate this with the same property? Set minus means intersect with a complement. So this would be A intersection B complement. So this minus this is this intersection complement of the second one. I'll put parentheses just in case, because I'm not sure what's coming. It's intersection B intersection B complement. Now what? I can erase, because of associative law, I can now erase those. Why? Because they are all intersections. So if it was union, then I would need maybe some distributive law or something. No need. So this was just precaution. Now I have no problems. What can I do now? Since I have 4 of them in that same intersection, I can reline them the way I want. So I get the intersection B first, this and this, plus A intersection B complement, intersection B complement. But what is this? This is a set, however you call it, but that's a set. And this is the complement of that same set. So according to the property that set times its complement is empty set, I get empty set, intersection B complement, empty set intersected with anything is empty set. Here's our final result in a way. All right, let me show you one very important example, and that is how do you disprove that 2 sets are equal? You actually, since proving that they are equal is universal statement, then to disprove something, you actually find a counterexample, as we learned in chapters 1 and 2. So here's my suggestion first. How do you find that counterexample? I like to use Venn diagrams. My suggestion is try as small sets as possible. Don't try something that's complicated to handle, but it's better something that has a minimal number of elements. So here it is. They say the following example, 3, 2, 2, and that is prove or disprove. So here it is, I don't know which way to go. That if A is intersection B, then A intersection B intersection C complement is empty set. So what do I do here? I will draw a most general Venn diagram that I have to. So assume, so A is intersection B, so I use Venn diagram. Completely generic Venn diagram looks like this, but this is not the case, ABC. Because I have the assumption that A is intersection B, so B cannot stem outside of A. So what do? So here's my A, no, here's my B. Here's my A. So A is subset of B. Now what? Be careful how do you draw C. Because basically there are 3 regions here, this, B not A, and it's completely outside. So most generic situation for C would be this one. So cuts a little bit of all three regions, 1, 2, and 3. So here's C. So where is, on my picture, A, this is actually A when you remove B intersection C. So A, when you remove B intersection C is this. So here is A. You remove B intersection C, and it's this. Okay. Does it need to be empty? Obviously not. So what should I do then? How do I design a counterexample? Generally, just make it sure that there is someone who's here. And I don't know what I put there. It doesn't have to be the same as in the notes. So generally, I put number 1 here. So make it sure that 1 is in A, and then of course it has to be B, but it's not in C. And then what do I do? In every region it won't hurt me. I'll put 2 here, 3 here, 4 here. Do I need to put 5 here, or this leftover might be empty? Either way. Let's say I leave it like this. So generally I see my sets. So who's A? A has 1 and 4. B has 1, 2, 3, 4, because B is all this. I count everybody that's in B. A subset of B, everything's good. What is C? C is 3 and 4. C has 3 and 4, and I didn't put anything extra. So let me see. So how much is B intersection C? B intersection C is 3 and 4. Oh, what I didn't do, I forgot to do that. I didn't put the universal set because if I have complements, I have to specify universal set. Who can be my universal set? Yeah, it could be even B. So if that's not bothering you, because there was no parts of C. So universal set, because everybody's in that universal set. Universal set is 1, 2, 3, 4. Because there's nobody standing out of it. So then B intersection C complement is everybody in universal set. That's not 3, 4. That's 1, 2. Okay. So A intersection B intersection C complement is how much? A has 1 and 4. This has 1 and 2. It's 1. And that's different from empty set. Here's counterexample. Here it is. So as I said, if I just write this, you would say, oh, how did he come up with it? Actually, you look in the Venn diagram and actually put the elements so that they justify what you did.